Hello, in this video we are going to talk about electrons. Last time we talked about neutrons and we figured out how to calculate the atomic mass for an atom or an element, and that was based on the number of isotopes that the element has and what the mass of each isotope is, how abundant it is, etc. And we talked about how you can find that atomic mass right underneath the chemical symbol for the element. So, for example, tin has an atomic mass of 118.71, and carbon has a mass of 12.011. But again, today we're going to talk about electrons. Now, the modern theory of electron behavior is called quantum mechanics. And that sounds really scary. We're not going to get into quantum mechanics, don't worry. But it does make the following statements about electrons in atoms. So electrons can only have certain specific energies. And therefore, we say that electrons are quantized. So instead of, for example, a slide where you have just a continuous set of energy levels, this is going to look more like a series of steps where electrons can only exist at these very specific levels. So that's what we mean by quantized, and hence the name quantum mechanics. So electrons are going to be organized according to their energies. Oh, I did not mean for my marker to be so thick there. That should be right underneath. There we go. So we call these energy sets shells. And they're given the label lowercase n. So for example, down below I have a picture of a lithium atom, and it has 3 electrons. The first 2 electrons are in the first energy shell, which is closest to the nucleus. So we're going to call that energy level 1, or n equals 1. And then the third electron is in a higher energy level, n equals 2. So generally, the higher the energy of a shell, the farther it is from the nucleus. So as we go further away from the nucleus, the energy increases for the electron. All right. So shells can actually be further divided up into what we call subshells. Try to say that 5 times fast. Subshells. So the first shell has only one subshell, and you can see that down below in this table here. Shell 1 has only one subshell. And the second shell has 2 subshells. The third has 3, and the fourth has 4. So pretty easy to remember the number of subshells, right? It's just equal to the shell number. And we do label each subshell, I'm getting tongue-tied, with the letters S, P, D, and F. And this comes from descriptions of how these subshells look when they're visualized. So for example, S stands for sharp. I guess electrons in an S subshell give a very sharp signal. I remember D stands for diffuse. So electrons in a D subshell have more of a diffuse picture, for example. So they do come from somewhere. They're not just random letters. So you'll notice in the first shell, we label that one S. The second shell, we label the first subshell as 2S, the second one 2P, the third one 3s, 3p, 3d. And in shell 4, we have subshells 4s, 4p, 4d, and 4f. Now, this can be confusing, so I like to think of this as an electron hotel. So let's say we have a hotel. Oh, well, the construction of this hotel is questionable. Let me fix the side here. And let's say this hotel has 4 floors. 1, 2, 3, and 4. So on the first floor of our electron hotel, we just have one room, and that room is 1s. And on floor 2, we have 2 rooms, 2s and 2p. On the third floor, we have 3 rooms, 3s, 3p, and 3d. And on the fourth floor, we have 4 rooms, 4s, 4p, 4d, and 4f. Now, in general, we're only really going to focus on those first 3 energy levels. So we're actually going to kind of ignore the 4th energy level for now. But you get the idea. And energy is going to increase from 1s to 2s, to 2p to 3s, to 3p, then 3d, and so on. So energy is increasing that way, if that makes sense. All right, now to add one more thing on top of this, each subshell holds a different number of electrons. So if we go back to our electron hotel, let me see if I can actually, oh, I don't think I can erase that. Let me redraw it on this slide here. All right, so I'm just going to draw the first 3 floors of our electron hotel. So we've got 1s, 2s, then 2p, and then 3s, 3p, 3d. So again, we're only going to focus on those first 3 levels. Now, anytime you have a room labeled S, that can only hold 2 electrons total. So maybe that's a smaller room. If a room is labeled P, that can hold 6 electrons. So maybe there's like 3 bunk beds in there. And then if a subshell or a room is labeled D, that can hold 10 electrons. So maybe that's like a big suite with several beds inside. So now we can start to figure out how many electrons go into each room. So again, in the 1s room, we can only have 2 electrons. In the 2s room, that can only hold 2 electrons. But the 2p room can hold 6 electrons maximum. And then 3s can only hold 2 electrons, 3p can hold 6, and 3d can hold 10. All right. So now, if we know how many electrons an atom has, we can start to fill in these rooms and figure out where those electrons are existing around the nucleus. So we mentioned before with lithium, we have 3 electrons. And we know that because lithium's atomic number, Z, is equal to 3. So that means that it has 3 protons and 3 electrons, if we assume that it's electrically neutral. So now the question is, where do those 3 electrons exist around the nucleus? And we said that the first 2 live in the first energy level, n equals 1. And then the last electron, the third one, lives in energy level 2. So that's going to be the same as these hotel floors. We have n equals 1, n equals 2, n equals 3. So the first 2 electrons are going to live on the first floor in room 1s. And then the third electron has to go into 2s first before we can put any electrons in 2p. So that's shown by this bullet point here. Electron filling always starts with 1s. And then we go to the next highest shell. So that's going to be 2s, followed by 2p, 3s, 3p. So that means we're starting at the lowest energy first and then just going up to the next highest energy level. So that's going to give us what's called an electron configuration. So we said that the first 2 electrons for lithium are going to be in room 1s. So we're going to write 1s with a superscript 2 next to it. And then the third electron is going to go in room 2s, and there's only 1 electron in that room. It's just staying by itself, so we write 2s1. So the electron configuration is 1s2, 2s1. So you can kind of think of this like if you're the hotel manager and you need to describe where all the electrons are staying for the night, or like which rooms are filled or not filled. You could just say in shorthand, there's 2 electrons staying in room 1s, there's 1 electron staying in room 2s. So 1s2, 2s1. So maybe that's your secret code that you share with the staff at the hotel. But anyway, that's kind of my way to remember the electron configurations and where electrons live at this hotel, right? All right, so let's look at another example other than lithium. So let's go to beryllium, which is the next element after lithium. So on your periodic table, try to find beryllium and figure out how many electrons beryllium has, and then try to write the electron configuration for beryllium. So you can pause the video, and when you're done, we'll go over it together. All right. So you might have noticed that beryllium on the periodic table has an atomic number of 4 right above it. So that tells us that beryllium has 4 protons. And if we assume that it's electrically neutral, how many electrons does it have? 4. All right. So now that we know how many electrons it has, let's look at our electron hotel, and we'll figure out where those electrons are going to stay. And again, we'll just focus on those first 3 energy levels. So we've got 1s on the first floor, and then on the second floor we have 2s and 2p. And then the third floor we have 3s, 3p, 3d. Okay, so remember the first room, 1s, can only hold 2 electrons maximum. So beryllium's first 2 electrons are going to stay in that first room. And then we're going to go to the next highest energy room, which is the 2s room. And that can also hold 2 electrons maximum. Okay, so that's a total of 4 electrons. So we're already done, right? We've got a electron configuration of 1s2, 2s2. Okay. And you can also double check if you've got the right number of electrons by adding the superscripts together. So that's 2 plus 2 equals 4. So we have all the correct electrons there. Now off to the side I have this little chart. Some people prefer this chart to the electron hotel. So basically in this chart they're listing all of the s orbitals right on top of each other, and then the p orbitals, subshells. In higher level chemistry we call them orbitals, but they're subshells. And then the d subshells and the f subshells. And then what you can do to remember the order of the subshells is to draw an arrow going through like this for each. So it's kind of diagonal through them. So you'll notice we hit the 1s subshell first, then the 2s, then 2p, then 3s, then 3p, then 4s. So if you want to think of it that way, you can, but if you want to just think about the electron hotel, that's fine too. Whatever works with your memory, because everyone remembers things differently, right? All right, so let's do one more practice together. Let's write the electron configuration for carbon. So if we find carbon on the periodic table, its atomic number is 6, so that's right above carbon. So that means carbon has 6 protons and 6 electrons. So now let's try to fill in the electron hotel. So again, we've got the first floor with 1s, the second floor with 2s, 2p, and the third floor with 3s, 3p, 3d. All right, so try this on your own first. See if you can write the electron configuration for carbon. And when you're done, we'll go over it together. All right, so let's look at how many electrons can stay in each of these rooms. So the first 2 electrons are going to go in the 1s room since it has the lowest energy. Then 2s is the next highest energy room. That can also hold 2 electrons, just like we saw with the previous example. Okay, so far we've used up 4 electrons. We have 2 electrons left, and they're going to go in the next highest energy room, which is 2p. Now, earlier we said that p rooms can hold 6 electrons, but that's a maximum. So if we only have 2 electrons left, they can still stay in room 2p. They're just going to have 4 empty beds, right? So that's okay. That's totally fine. Maybe they're going to bring some friends over later. All right, so let's write the electron configuration. So 1s2, 2s2, and 2p2, because there's 2 electrons staying in each of those rooms. All right, so hopefully that helps a little bit with figuring out where electrons live around a nucleus. And you are probably going to notice a pattern if we keep on going down the row of elements. So, for example, if we look at the left side of the periodic table, the first 2 columns, those are all going to end in an s orbital for their electron configuration. If we go over to the right-hand side of the periodic table, each of those elements' electron configurations will end with a p. And then don't worry about the middle here. or these two rows down here. We're not going to cover those this quarter. We're just going to focus on these first three rows. All right, so let's actually look specifically at boron through neon. So the right-hand side, row 2. So boron is going to need spots for its 5 electrons, right? So the first 2 electrons will be in room 1s, the next 2 will be in 2s, and the last one will go in room 2p. So it's 1s2, 2s2, 2p, 1. Now if we go to the next element over, which is carbon, carbon has 6 electrons, so it has 1 more electron than boron. So we're just going to put that extra electron in room 2p. So now it's 1s2, 2s2, 2p2, just like we saw on the last slide. Now, nitrogen has 1 more electron than carbon, so that electron will also go in room 2p. So now nitrogen is 1s2, 2s2, 2p3. And then we can keep going because we're just going to add an electron every time we move over an element, right? Now, once we fill up that 2p room, so let's say we're looking at neon over here. Neon is 1s2, 2s2, 2p6. And let's say we jump over to the next row and look at sodium. Sodium has 11 electrons, so 1 more electron than neon. So now we need to fill in the next room because 2p is full, so we're going to fill in 3s and put 1 electron in that 3s room. So hopefully you're starting to see the pattern with electron configurations, but of course we'll get more practice later on. So why do we care where electrons exist around the nucleus? What is the big deal? Well, the reason we care is due to something called valence electrons. So in chemical reactions, we're either going to see atoms share electrons or they're going to transfer electrons between each other. So that's going to happen between the highest energy electrons. So the highest energy electrons will either be exchanged or shared, and those are called valence electrons. So that's why we care where the electrons exist around the nucleus. So, for example, looking back at lithium down below, we said that the first 2 electrons live in room 1s, in the lowest energy room, or subshell. And its 3rd electron lives in 2s. So that's going to be our highest energy electron, the one that lives in the highest energy subshell. So that's called lithium's valence electron. So once we're able to figure out where electrons live or what energy they have, we can then narrow down which electrons have the highest energy and therefore what they're going to do in a reaction. So for example, let's determine the number of valence electrons in each of the following. So if we start with boron, which we saw earlier, the highest energy level in its electron configuration is energy level 2. And we can figure out how many electrons are in energy level 2 by adding the superscripts together. So 2 plus 1, oh, whoops, I wrote 2 plus 2. That should be 2 plus 1 equals 3 valence electrons. And that's going to be true for each of these elements. Their electrons are all going to exist in energy level 2. They're valence electrons. So we can just add together these superscripts for each element. So for example, carbon will have 2 plus 2, 4 valence electrons. Nitrogen will have 5 valence electrons. Oxygen will have 6. Fluorine will have 7. And neon will have 8. So again, this is going to really help us better understand how atoms are interacting with each other when they react. So I'm going to stop there today. We'll pick this up in the next video and talk more about the types of elements we have on the periodic table. So I will see you then.